Hey everyone, we're going to finish the last section of chapter 1, and I decided to make it a video lesson so you guys can get some practice hearing my voice and making sure everything's running smoothly. So this last section covers a term known as homeostasis. This may be a new term for you, or it may be a term that you've heard in biology, so you may have heard it. Homeostasis is actually the maintenance of stable internal conditions, even though the outside world is always changing. So what I mean by the maintenance of internal conditions, well, conditions can be things like your pH level, your temperature. It could even be your glucose level or your sugar levels in your blood. You want to make those oxygen levels. Anything that has to do with helping your body run, we usually like to keep them balanced. Your book describes homeostasis as a dynamic state because homeostasis actually kind of means the same or not changing, and that's actually untrue. Instead, your body changes all the time. It's dynamic. So your temperature can range, and you're still considered healthy. So your internal conditions change, but they vary within narrow limits. So typically you want your temperature between two certain values. If they get too high, like you run 100-degree fever, that's not a good sign. Or if they get too low at like 94, 95 degrees, that's also outside of those limits. So again, they can fluctuate, they just stay within narrow limits. This is extremely important for body functioning to happen, normal body functioning, I should say, and to help you sustain life or keep alive. It's extremely important. Your book does like to say that in general, your body demonstrates that it's in homeostasis when its needs are being met and that it's functioning smoothly. Okay. So homeostasis, how is it maintained? Well, every organ system has to play a role in maintaining homeostasis. Like we said in the very beginning, all of these things work together. They need one another. In fact, there are two systems that stand out above the rest, and that's because they're communication systems. They help control the rest by saying, hey, you need to pump more blood because I don't have enough oxygen. So remember, nervous system we learned about, and the nervous system receives signals, and then they send signals because they process that information. And the endocrine system, they are in charge of releasing hormones to cause a response. So use electrical signals, that's the nervous system, and it's delivered by nerves. Or hormones can be sent by the endocrine system, and these acts as information carriers. So for example, if you're too hot, it would send a signal telling you to start sweating. Now, whenever homeostasis gets thrown out of balance, we have something called a homeostatic imbalance. And this is the disturbance in homeostasis where it becomes out of that zone that you want to keep it in. And this can result in some diseases. So if, for example, your temperature is above normal range, it's 102, there is a homeostatic imbalance within your body. So maintaining homeostasis. All homeostatic control mechanisms have at least 3 components. You have a receptor, a control center, and an effector. So a receptor is going to respond to changes in the environment. So this is called a stimuli. Some examples could be like your eyes seeing a really bright light. That bright light can be a stimulus. The smelling of food can be a stimulus. Maybe inside your body, it detects that you're thirsty. So then it's going to cause you to drink water. So it's going to take in all of these stimuli, all of these different things happening. And it's going to send information to your control center. And it's going to go along the afferent pathway. And this is actually an important term. You'll be quizzed over it. The afferent pathway goes from the receptor to the control center. So in other words, the book like to say, think of afferent, and the A in approaches. So it approaches the control center. Next, you have the control center. It's going to receive those signals from the receptor, and it determines that set point where things should be set at. So you should have a 98.6 temperature or around there. It's going to analyze information. So it's going to analyze everything that it receives. And then it's going to determine the response that it wants to give. Should it make you feel thirsty? Should you start sweating? Should you actually get goosebumps in order to cool back down or warm back up? My bad. Things like that. And what it does is it sends this response to an effector. So it provides the means for the response or causes you to do the stimulus. Maybe if it's light outside, the effector will cause your eyes to contract, so not as much sunlight is getting into your eyes. And the information goes from the control center to the effector along the efferent pathway. Your textbook likes to say, think of the E in efferent with the E in exit. So it's exiting, it's going away from. In fact, you're going to hear the word afferent and efferent again when we start talking about the nervous system, and even when we even get into blood vessels. So here are the three major parts of the homeostatic control system, along with the afferent and efferent pathway, so you guys can have a little visual. So let's go by one, step by step. First, you get a stimulus. So this is where you are balanced. When you get a stimulus, you become unbalanced. Oops. The receptor is going to detect that stimulus or that change. So maybe there's too much light. And it's going to send that information along the afferent pathway. So it's going to tell your control center, hey, my eyes are getting too much light. It's too sunny. The control center is actually going to make a response, take in that information, and decide what to do. So it's going to send that information out along the efferent pathway to the effector. And the effector is going to basically try to reduce the effect of the stimulus. This might be contracting your eyes. It might be closing your eyes. It may be, okay, hey, I need to put a visor down or I need to put sunglasses on in order to get that back into a homeostatic level. Another example is your temperature. So here, stimulus would be you're getting too hot. The receptor is going to detect that your body's getting too hot. It's going to send that information to your control center, and your control center is going to decide what to do. It may send a signal to your sweat glands. Your sweat glands would be the effector, and it's going to cause you to sweat in order to cool back down. Now, there are two different feedback mechanisms. The first one is negative feedback. And in fact, most homeostatic mechanisms in our body are negative feedback. What they do is they shut off the original stimulus or they reduce the intensity. So these are the examples I've been using for if it's too sunny or if the temperature in your body is too high. Again, it's going to work like a thermostat. Your thermostat likes to stay within a certain degree. I keep mine at 68 degrees. So if it gets too hot, it's going to detect that change. It's going to send it to my thermostat control center, and that control center is going to send out and decide to kick on the air if it gets too hot. If it gets too cold, it's going to go to my control center. My control center is going to kick on the heat to bring it back up to that set level. So a lot of examples of negative feedback are heart rate. You want to stay within a certain heart rate. Blood pressure, if you go to the doctor, that's one of the things they always take. Breathing rate, your release of hormones, blood levels of glucose or your sugar, blood sugar. If you're diabetic, they want to keep that within a certain level. Oxygen, carbon dioxide, even minerals. The opposite of negative feedback is positive feedback. This is actually rare in a human body, but there are some positive feedback that we see. What positive does is it increases the original stimulus to make it, you push it further. Usually these reactions occur at a pretty fast rate compared to a lot of the other mechanisms in your body. Some examples include blood clotting. So once you start clotting, positive feedback is going to make you clot faster or send more clotting proteins to make you form a clot. Also, during the birth of the baby, once you start contractions, you'll notice that positive feedback will increase that stimulus. Those contractions become stronger, they become quicker, they occur faster and faster until you birth your baby. So here's a question I want you to try to answer, and then actually come up to me and tell me what you think your answer is going to be. So when we begin to become dehydrated, we usually get thirsty, and this causes us to drink liquids. Is this thirst sensation part of the negative or positive feedback? So think about what's happening and defend your choice. So come up and tell me what you think. If you have any questions over this lesson, please let me know, and I hope you have a good day.